So this is Hao Zhu, and so he and Zoey Greer are going to present towards a parallel and restartable data transfer mechanism in iRODS.
Okay, thank you. So I'm just going to get started. So what I'm going to talk about now is kind of a prototype for what will happen next. So I'm going to talk about the design of the system first, and then Zoey is going to demo a kind of work in progress. So some of the stuff that I'm going to talk about is still kind of in the design phase. It hasn't been implemented yet. But what Zoey has implemented is very, very nice. So she'll show you later. OK, so here's some of the things that we're thinking about when we're designing this new mechanism. So first of all, we don't want to just restart the whole thing, redo the whole thing, right? So we want to kind of build on top of the existing ICAT design, which works pretty well for a lot of people, right? So we just want to add the features that people want without taking away the existing feature away. So one of the most important thing I think is for this design, I push really hard is the put-get replication symmetry. So currently we don't have this symmetry in our design, right? When you put, you get, you replicate, they don't naturally go to the same low-level API. They do share the API to some extent, but we want to really push that symmetry to the full extent so that it's 100% symmetric. So also we want to build API on top of small services instead of having large monolithic APIs. And we want to also support parallel transfer, distributed transfer, parallel replication, all these things that's parallel and restartable. That's also kind of the consequence of having that symmetry. So if you make one thing parallel and restartable, and both the other two operations will become parallel and restartable. So last but not least, we want to support distributed storage of ICAT. So we want to kind of build the concept of locality into where we store the metadata about these things. So we can easily retrieve those metadata without having to, if you think about running a distributed key value store, you don't want things to be replicated to the other nodes of the database all the time. Okay, so this is the current design. It's very simple, from conceptual level, you have multiple replicas of one data object, and you have one replica per resource. But the limitation of this is the way we do, if you want to do restartable or parallel transfer, chunk transfer, multi-part, it's basically ad hoc, right? You create parts, there's information about parts, and after you're done, those information gone. They're not in the metadata catalog, right? So here's a new design. The new design, we just added one more entity called blocks. So now each data object can have many blocks, and each replica can contain many blocks. Each replica doesn't even have to contain all the blocks. If you can kind of think about many different ways of this can be combined, and that will create the opportunities for a lot of these applications. Okay, so now with the introduction of block, we have a block level API. So the block level API I'm going to present today is very simple. There's just put and get, right? So then there are three directions. There are client server, server client, server to server, right? So apparently you don't want clients to clients probably aren't be able to talk to each other directly. So the second row is no, but the first row and third row they can all be yes. But we don't need server to server get for this. The current version of the design, but we're evaluating different design choices. And then, based on this block level API, we just built the object level APIs so that we can have that symmetry between put, get, and replicate. Right? So here's some data types. I'm going to skip this slide. So next, I'm going to talk about some of the operations that in an API. So first is block put. Very simple. From one place to, you just put a block to a server. That's it. So you can call this from a server. You can call this from a client. Same effect, symmetric. And then you have a data object. This is basically you call the server, and the server returns to you the metadata about this data object, including what are the replicas and what are the ranges. Ranges tells you what blocks are on this replica. So there's some more details about this design. It's not as it looks like, but I think because of the short talk, I can't get into details. So the details has to do with fault tolerance, right? But if you guys are interested, I can talk about to you after the talk. Similarly, for each replica, you can call this API to get the metadata. And then last but not least, you have the opposite direction. You have the get API. So here is a kind of a sequence diagram of how you would do this to do a put, right? You first, as a client, you connect to any server you want, right? You say, oh, I want to put a object. Then you connect to server 1, and server 1 tells you the metadata. He says, server 1 basically says, oh, these are the replica. This is where I want you to put it, and this is the range where I want you to put it. And then, okay, so then the client go to the server 2 and ask for the metadata about that replica. Server 2 may return, oh, I already have blocks 0 to 64. I don't need those blocks anymore. So then the client can say, okay, I'll just give you 64 to 128. So this is the example where you can restart, right? So if this is a new replica, server 2 would tell you, oh, I don't have any blocks, then you just send all the blocks. But if server 2 says, oh, I already have these blocks, you don't have to send those blocks anymore. You just send the other blocks. Similarly, remember symmetry, I mentioned multiple times. So this is the get. So it looks very similar to put, right? You do the same thing. You send server 1, say, I want this data object, like tell me the metadata. The server 1 tells, oh, the server 2 has these blocks. Then you go to server 2 and ask, oh, what do you have, right? Server 2 says, I have all the blocks you need, right? Then when you come back, you know you already have the first 64 blocks, then you don't need to request those 64 blocks anymore. You just say, I want the 64 to 128. So similarly, you can do replication. The replication, the reason is a little bit complex is because it's actually, you have to have the client to initiate this process. But once you cut the client off, it's kind of basically symmetric to the other two use cases. So this is also symmetric. This is how we store a partially a replicated object or a partially downloaded object, partially uploaded object, same data structure on both server and client side. You have the blocks, and then you have the metadata. So this metadata is local to the host. So when you query the metadata, you don't have to go through the remote database. So here's an example of parallel get. So you have two replicas from two servers, potentially. And as the client, you can just request them. Then you have parallel. This is parallel put. Sorry, this is parallel put. You can put. So because they are so similar, so symmetric, it's hard to remember which one is which. So you just reverse the arrow. Now you get parallel get. So well, there's a small difference. When you do parallel get, you do have to keep the metadata. But when your get is done, you just truncate the metadata. Then you get the whole file. In the metadata part, we're exploring the design of the right type of checksum. So because we want it to be fast, so we're not going to use cryptographic hash functions, things like that. We'll probably use something that's pretty weak cryptographically, but it's good for checking the errors. We will do block level checksum. Yeah. Sorry, can you repeat? I didn't hear you clearly.
So I was wondering how you're going to handle the dirty replica state while the replica is being updated. Because while you start pushing blocks to a replica, that replica is by definition newer than the others, but it's not clear which one has the right data until you finish doing the write. But you could still be pulling from that replica. You know, if you just pick a random number of replica, you're putting something that's potentially inconsistent. So how is all of that handled, and how is it reported in the CLI, for example?
Okay, so that is a very good question. That's the fault tolerant part I was mentioning that. So the basic idea is we do have a unique ID for each version, the replica, and when you do a partial, so when you try to download or upload data to a replica, remember I have object level. The sum server will tell me that this replica has 1 to 2, like 100, all 128 blocks, right? But I don't trust that information. I go to that replica, ask what exactly blocks do you have. So if you have a dirty replica or partially dirty, whatever, it can look up this information, this unique ID. It says, oh, actually I'm in a process updating, so I only have new blocks for like first 64 blocks. And then you use the second, the information returned from the second call to determine what you do next. So we can talk more afterwards, yeah. Okay.
Anything else? All right, so now we're going to have a demo of this magic, right?
Yeah. Okay, so the current state of the code is we have multi-part transfer between clients and servers. We don't have any of the other fun stuff that Hao talked about. We have restarts on both puts and gets. We can currently reconstruct blocks on the other side. So we don't, on the server side, so we don't actually do the separate table yet. And this is a table of values for purely local puts that I did to compare speed, because if we have a speed up, then that's nice. Though honestly, most of the rest of the design is more important than speed, in my opinion. But as you can see, for actual puts, and this should say gets for the this part right here. Look at the magic. Oh no. There we go. Fix this over here. Okay, yeah. So for puts, it's at first not very big of a difference. And this is for a machine that has a lot of processors, because the parallelization matters a lot for this. But for my machine, I managed to get a 45% speed increase for puts and a small but not completely insignificant speed increase for gets. Now, I'm going to show you how it looks when it actually works. Assuming that it actually works. Yeah, how about we save those? Sure. Okay. So this is a VM we have at Rency right now. I'm just going to hit up until I get to the commands I want, so that I don't mistype them. So that there we go. Yeah, look at that. Okay, so this will do put with 4 threads in 4 parts. And let's, ILS first to demonstrate. I don't have anything up my sleeve. So this will take like about 9 seconds. Because the VM is not fast. This takes like less than a second on my actual machine. Oh, this is a get. Well, it'll take forever. Let's do a put. I got the put the first time, and then I was like, oh, let's do an ILS, and yep. So let's do that. And we can even interrupt it, I guess. Well, I can't interrupt it because I'm not good with Macs, but I would have been able to interrupt it. I'll interrupt the get, probably, assuming I know how to do it. So now it's not immediately constructed on the other side, though now it is. Initially, as Hao was saying, it puts a bunch of data objects together right now, and then reconstructs all the data objects out of a directory. It does that pretty quickly, but it doesn't do it synchronously with the actual put, which is part of the speed increase that you're seeing, is that like we're not actually bothering to put the whole file together on the other side before you've disconnected for the data transfer. But it also just is a faster transfer in general. So now we can do the get, and assuming I can Control C on a Mac, I can show you a restart. Oh, okay. That did not look like a, oh, I think I did. Yeah, cool. Okay, so now if we look in this directory, it has this file that's horrifyingly named to let us know that that is exactly the file that we want to get back to with restart. And we can look at the progress with a tool I made to let me look at all the progress and see the basically the chunk of metadata that I was talking about at the bottom of the file. So progress inspection on 0 and tab, enter. And so we can see that it did 50 parts in each one of it, or sorry, 50 blocks in each one of its parts. And the blocks are 4 megabyte size blocks. And so then we can restart, and it'll just pick up right where it left off. No, if you change the part, well, if you change the threads, it'll restart the same way because the threads don't matter for that. But if you change the number of parts, it will not restart in the same way because it can't. The way that all the metadata is stored right now doesn't allow you to do that. I'm not sure that's necessarily the best design. I'm going to probably talk to Hal a bunch about exactly what we want that metadata to look like. But yeah, anyway, for now, you can see it took 6 seconds to do the rest of the transfer, and it originally took like 8 or whatever for the put, so 2 plus 6, 8-ish. Oh, and I was going to diff the files to demonstrate they were actually the same. Right. Oh, let me like show you that they're actually 2 gigabyte files too. I'm not just like, oh look, here's a 2 gigabyte file, it's 0 bytes. Yeah, so for those of you conversant in powers of 2, that is 2 gigabytes. And now we'll do the diff. 2 gig dot bytes, and then the 2 gig dot get test that I made. Da-da. Hooray, we didn't have like a quantum bit flip. That's good. That would have been a real shame. Anyway, so any questions for me?
Did you test it at distance?
I have tested it at some distance, not really far distance. We tried to do stuff at TAC and Cyverse, but right now the code does not handle long latencies as well as one would like. There are crashing problems around ZMQ right now, so Jason got it to work at some distance and got good numbers, but I don't actually have his numbers. So if you want to know how it worked for him, you know, talk to him. Okay, hey.
So how do you verify, which byte you ended up and which byte you were picked up for your next hit?
Oh,
You have to verify that with the file.
right. So that's the thing Hao said. There's a metadata field basically at the bottom. Right now, it's really just it's like the number of parts in longs, and the longs list exactly how many blocks have already been transferred for that part. So when you do the get again, you just see how many parts have been transferred, and you always transfer parts sequentially, or excuse me, blocks been transferred for a part, and you always transfer blocks sequentially. So if I see that there are 50 blocks that have been transferred, then I know that I've already transferred the first 50 blocks of that part, and I only need to get the next 53 or whatever. Yeah, sorry, next 78 in this case.
You're just possible because you build up another package you're not verifying.
Hmm?
What exactly you did.
The verifying is you have to do with checksum separately, basically. If you try to verify stuff at every step, then you end up with extraordinarily slow software, which makes people upset. So you have to either have blocks set up to be able to be checksummed directly, which you can do is slow, but you can do it, or you can just verify. You can run a checksum at the very end and make sure the file is the same as the file on the other side. Might be a question about data moving underneath you, and that's part of what the ridiculously long file name is for, is that if the file has moved at all since you last tried to do a get, if you try to do another get, it will ignore that file because that file doesn't match the new file, even though it's the same name as far as iRODS is concerned, because it'll have different timestamp, different checksum, different whatever. It'll know that it can't continue from a file that's changed. So that's not exactly your question, but.
So for some kind of file, you lost a couple of bytes, okay. But for some, something like a text file,
Mm-hmm.
you lost one byte, then you get this kind of random, characters. If it's image, that's okay. You copy your resolution to be higher or lower. But for the text, if you lost one byte, then you have to send back.
Yep, and then you have to either do some sort of verification, like do checksum verification on individual blocks, and you can make the blocks large, and then you can do partial synchronization, which is the other thing that multipart gives us as an option, so that you don't have to get the whole file back. You'd be able to get just the part that messed up, or if the file if you somehow actually missed bytes, which I don't think you can do, as opposed to just having the wrong bytes. If you'd somehow lost bytes in the middle of the file, you'd have to transfer the whole file again because you wouldn't have the separate parts. But you can't really do that because the program transfers things in blocks, and if it transfers things and determines that the block isn't the right size, then it won't continue at the wrong offset. It'll just throw a fit and make you restart stuff. So, anyone else? All right. Good to talk to y'all.